So, our first talk is by RMS. Welcome, Richard. Called Ruby Silence.
Okay, I've got 326 slides, so let's go. This is my first PHP conference. I'm really super happy. First time I've ever used PHP. People call me Schneeman. My last name is Schneeman, and I love Ruby. You might be familiar with Pee Wee Herman, who famously said, "Well, if you love it, why don't you marry it?" So I did. So this is my wife. Her name is Ruby, and she is actually a Python developer. Funny enough. So we recently got pregnant, which we're pretty excited about. And I don't have time for clapping. You're gonna have to cut that out. So I suggested a couple names. I was like, well, if it's a girl, we should probably name her Pearl. If it's a boy, I'm thinking Haskell. It's like, you know, we just get made fun of like crazy. Either way, I think kind of a gender-neutral name would be pseudo. So you could be like, pseudo, clean up your room. Okay. So I work for Heroku. I've got commitment on Rails. I run a conference called Keep Ruby Weird along with Terrence Lee and a couple gentlemen from ThoughtBot. Okay, so I'd like to set the stage. The year was 1987. Full Metal Jacket, Stanley Kubrick's great kind of anti-war movie, which introduced, of course, the famous phrase you might be familiar with. Is anybody familiar with this movie? Yeah. Okay. So this is my README. There are many like it, but this one is mine. The great coder mantra. Also, 1987 brought us Lethal Weapon, Spaceballs, and my personal favorite, The Princess Bride. Yeah. Oh yeah. So. Really though, 1987 was the year of 87A, which is a specification that was introduced by CompuServe. So 87A was a really convenient way to compress images and share them. You might know it as this.
GIF. Yeah.
Okay, so moving along into 1989. A new specification, well, actually 1989, of course we know is the year of Taylor Swift. You can shake it off. The new specification of 89A was introduced, which gave us animations. And eventually, more advanced animations. So originally the animations only played once. Netscape Navigator 2.0 introduced the ability to have looping. And you could say that in this time it was kind of the golden age of animations, and times were good. As a matter of fact, I think times were great. So, okay, what does this have to do with programming? You're probably like, I have no idea. All right. I want to talk about linguistics for a little bit, so we're gonna switch tracks and come back to that. So linguistics is the study of language, which some of you might have heard this applied in a computer concept. Generally, as with programming, we are typing a language for our computers as well as trying to communicate with other programmers. Of course, everybody knows the two hardest parts of programming are cache invalidation and naming, and I1 errors. Okay, so in linguistics, there are two types of linguistics, two general types of linguistics. There are descriptive linguistics, and the best way to describe descriptive linguistics is with this example. Ain't nobody got time for that. So this is something that people say. Ain't is a really common part of the English language. If you listen to news, if you're on the internet, you will hear people say ain't. So if you were going to be describing the English language and describing the linguistics of it, you would say that this is part of the canon of the English language. You're basically using it to describe how other people use that language. The other kind is called prescriptive. If you've ever heard the phrase, ain't a word because ain't in the dictionary, you're basically prescribing that you should not be using this word because it wasn't originally intended to be a word. Ain't is not valid. So we have descriptive and we have prescriptive. So prescriptive linguistics essentially are talking about how things should be in the world. All right, all of this brings us back to girl, gift, give, gigabyte, and gif.
Woo. Yes.
Or gin, gist, ginger, gif. All right, who says gif?
Yeah.
Okay, gif. Okay, we're pretty much evenly split. That's
good.
so we can have a battle royale later. We'll see who's stronger. So, which one of these is correct? We have it's pretty difficult to tell. This gentleman, Steve Willett, in kind of a thank you speech, he was part of one of the original creators of the specification, and in the speech where they were saying like, hey, thanks for giving me this award, he actually mentioned his disdain for the wrong way, and also mentioned that in CompuServe, people, whenever they were asked how do you say it, they would respond with choosy developers choose GIF. So with a soft J. And right now, this is actually, it's in the dictionary. GIF is in the dictionary, and some dictionaries list both ways of saying it. Some say it with a hard G, some say it with a soft G. Some have like one before the other, like this is a hard G, this is a soft G, and I mean, so basically nobody can agree. This guy says it's not okay. Some dictionaries say it is okay. And I think this is kind of interesting because generally most people treat programming as exercises in truth. If we do this operation over and over again, so 1 plus 1, we will always get 2. And because of this, we treat programming as unambiguous. We take specifications and we either deliver the right product or we deliver the wrong product. So maybe programming isn't always, maybe if your specification is unambiguous or is ambiguous, then your product is also ambiguous. Okay, so a practical example. Rails M. You all familiar with Rails M? Okay, so Rails M, valid Rails M's are production, test, and development. And as a side note, this is kind of on a tangent, staging is totally not a valid Rails M. If you've ever used staging as a Rails M, you should feel bad. And some really simple examples, because you will have like this in your code, and then you'll deploy to staging environment, and then your server will be like, oh, there we go. Okay. Okay. Or you have groups in your gem file where you're like, hey, production group, and then you deploy that, and you're just like, I don't know why this isn't working. What's going on? Okay, so if you have something like this inside of your code, you're doing it wrong. Instead, I would recommend doing something like this, where you are just pulling what you need from an environment variable. A way to think about it is that your staging server is actually running in a production environment. So, okay, end tangent. Yes, that was prescriptive. You're very astute in gauging that. And just as a gentle reminder, if you do use it in staging, as staging, then like you'll experience pain. Maybe not today, maybe not tomorrow, but like this is something I get as a ticket in Heroku like all of the time. Where it's just like it's not working, and they're debugging for like literally days or hours. And okay, so that's that. Back on to topic. Has anybody ever heard of RackM? Okay, so valid values of RackM, production, tests, development? Maybe? Seeing some kind of like No shaking hands. So if you go to github.com /rack, the only place it really mentions this is one tiny example documentation where it mentions that the environment for rack valid values are development, deployment, or none. So if you're using production inside of your rackend, it's not technically correct. The most popular rack micro framework, of course, would be Sinatra. And if you go to Sinatra's documentation, it is going to tell you that you should set your rackend to either development, production, or test. So this is the most popular consumer of Rack directly. And I said micro framework because technically Rails is also running on Rack, but I wouldn't really classify Rails as a micro framework. So which is it? Which is right? Production, test, development, or should we be using deployment? Here we have a scenario where we have two people telling us very different things. Is it GIF? Is it GIF? The specification is saying one thing, and developers have for years been using a different thing. And it's just a case of, are we doing the descriptive thing of using what developers are actually doing, or are we doing the prescriptive thing of looking at the specification and saying that is what is right? So on Heroku, and we've been doing this for years, we set Rails end equal production as well as rack end equals production. And I'm not saying that this is right. This is actually, it's kind of a giant conundrum, something that's only relatively recently come to my attention. Unicorn actually expects the specification. And if you're not using deployment, then you're gonna have problems. Of course, Sinatra expects what they claim in the README, and if you're not using that, then you're also going to get problems. So if we just swapped out things, like today, if we're just like, hey, we're going to use deployment instead of production, then people's apps would break. If we keep on doing what we're doing now and keep on using productions, people's apps are also going to break. So it's kind of this no-win scenario, and there's not really an easy upgrade path. So I just want you all to meditate on that for a second. Did I mention how much limited time I have? Okay. Who here has a computer science degree? All right. I don't. I do not have a computer science degree. And I want to introduce you today to someone else who does not have a computer science degree. This is Benedict Cumberbatch. He's an actor famous for playing Sherlock Holmes as well as recently Alan Turing in Enigma, The Imitation Game. Also, funny enough, the person he was playing, Alan Turing, does not have a computer science degree. He kind of invented computer science. So, has anybody seen the movie?
Yes.
Yeah, it's pretty decent. So, I want to talk a little bit about the life and time of Turing that wasn't really talked about in that, so you might learn something new. Basically, Turing was born into sort of the golden age of mathematics. He was a mathematician, very much so. Von Neumann, Hilbert, Gödel, I hope that's right, Einstein, Gödel, Gödel. All of the above. GIF, GIF. So, I mean, it was this really interesting time because there was all of these theorems from decades or centuries where they had just been unsolved, and all of a sudden one person makes one discovery and they're like, holy crap, now I can solve this other theorem, and now I can solve this other theorem. So for every theorem that somebody figured out, there was a new door and more questions. And it was actually in this time, and I always thought quantum mechanics was like a relatively new thing, but apparently that came about during Alan Turing's time. So quantum mechanics was introduced. And there were real-world benefits, like cryptography. Maybe some cryptography was better than other cryptography back in the day, but it was really, really interesting time to be doing math and to be working on these types of problems. And the type of math that I'm talking about is not like 1 + 1 or 3 divided by 4. It's like it's almost philosophical math. For an example, this is Goldbach's conjecture. So Goldbach said that every even number can be expressed in the sum of two primes. For example, 4 is an even number, and we can express it as 2 plus 2. 2 is prime, and 2 is prime. 100 is even, and we can express it as 3 plus 97. So, like, that kind of makes sense. You're like, all right, I don't see how that's beneficial or practical or, worthwhile. But these types of things in math have a surprising way of, once you can prove this, then you can use this proof on other proofs. So it has this kind of snowball effect. So in Goldbach's conjecture, we will ask the question, okay, well, it looks like it's right, but how can we prove it? One thing we could do is a mechanical calculation. We can see that this is valid for the number 4. We can see that it's valid for the number 100. And you know what? We can write a computer program and we can just keep on going. And people have done this calculation up to this really large number. But guess what? This is not every even number. Even if we raise this number to the power of this number, raised to the power of that number, raised to the power of that number, it's still a finite number. So in order to prove that this is valid for every number, we have to do a little bit more than a simple mechanical calculation. On the surface, it looks like a really, really simple problem, but in reality, there is no accepted solution. Like this conjecture has been around for a really, really, really long time. Several people do actually have proofs that they claim they have solved it, but they are so complicated, no one else can understand them. Like, that's pretty complicated. All right, does anybody in the room speak German? A little bit? Okay. Could you pronounce this?
Entscheidungsproben.
Entscheidungsproben. Okay, good. Thank you for the audience help. I love German because you can just like mash up words and make new words.
Yeah.
It's amazing. So my last name is Schneeman. It's actually German for snowman, if you didn't know. I did not just make that up. So this roughly translates to decision problem, and this is a problem that was introduced during Alan Turing's time. The decision problem is described as, given a distinct mathematical problem, do we have a process that can exist that will tell me whether or not this problem is solvable? Can we solve it? There are mathematical problems which, for Goldbach's conjecture, it might not be solvable. There might not be a definitive yes or no answer, and that's kind of okay. And this is an interesting question because at the time, mechanical calculators were just becoming in vogue, and mathematicians were kind of wondering, philosophizing to themselves, am I going to be obsolete? Is all of this hard, like they just go and they just think really, really, really hard, and then they come up with an answer, and they're just wondering to themselves, am I going to be replaced by some sort of a process, some sort of a calculation? And back in the day, calculators were actually people. They would just give them a set of calculations to make. So, does a process exist that can tell me if a problem can be solved? On the surface, you would be like, well, no, there's not one universal process that can do that. So, unfortunately, that's not a valid answer. The hey, that doesn't sound reasonable is not accepted in terms of math proofs. So, somebody had to prove it. And basically, we want you to start from nothing and imagine a machine capable of solving just everything, anything. And Alan Turing managed to do that. Surprisingly enough, he was actually the second person who did it. The first person invented lambda calculus, which is really funny that solving the same problem, you get two massive contributions to computer science. So I think that's interesting. Taking a look at how he did it, it wasn't necessarily pure brilliance or dumb luck. He didn't just kind of trip over something one day and be like, hey, I've got the lightning didn't strike his brain. He didn't brute force it. He didn't do a whole bunch of mechanical calculations. Personally, I recommend if he was to do this again, he probably should have read this book because I did, and it was just, the answer was like literally right there. I mean, come on, he wasn't even thinking. Alan Turing, throughout his entire childhood, had a very innate and natural curiosity. When he was a child, he was constantly getting in trouble for doing things like, showing up home with like his clothes ruined because of some like failed science experiment that he just decided to embark on. And he had a real love of science, and for him, science meant a doubting of the axioms, basically taking a look at what already exists out there and being like, well, what if that's not true? What if we could do something different? So, in order to solve this problem, he actually did invent what we now consider the practical model of a computer. And he didn't intend to do that. Instead, what he wanted to do was solve this very practical, very pragmatic problem that was interesting to him. He was focused on a real-world, this math problem. And to him, if he could do this, if he can solve this, it actually means advancement to the field of mathematics. So he authored a paper called Computable Numbers. In this paper, he introduced the concept of a machine. It's like a typewriter, but with infinite paper. It can write, it can read, it can erase. And if it looks familiar, it's because it is. It's like a computer. It literally is a computer. If you are familiar with Rails or any kind of web interfaces or databases, create, read, update, and delete, this is essentially the same thing, except for update is just like erase and then write. It's like a two-part. So, in theory, there's nothing computable that this machine cannot solve. Like, everything known to mankind, provided that we can read instructions and write them out with this machine, we can do. So the answer is yes. All right, we have this model and we have this idea for how to solve everything and that is calculatable. But can you be sure? Can we be really, really sure? And this is actually where the answer came from. This is a slightly simplified form of the Computable Numbers paper, but the real answer comes from how would you be sure that your machine really can compute everything? You know, those three, it can write, it can read, it can erase, but like, what if there's secretly a fourth one that we don't know about? Or that is super critical, that after you can do that, then you can compute everything. With Goldbach's conjecture, we tried just putting in a whole bunch of inputs and testing them with the outputs, and that wasn't valid. So with this machine, we can't just say, here's a whole bunch of mathematical proofs, is this machine valid or not? So really, the only way to check the validity of the machine would be to actually run the machine against itself. Like, have a valid machine already, and then take all of the inputs from that machine and put it into this one and verify that they all matched up to infinity. Unfortunately, we can't do that. It would kind of be like asking a student to grade their own test. Like, you can do it, but there's no guarantee that the answer is going to be valid. So, Alan Turing, because of this, decided that, okay, yes, the problem is solved, and the answer is provably and definitively no. So that was kind of nice. So it was interesting because he accidentally created the general purpose CPU, and the model that we use today to define a computer. And yes, he went on to go and do lots of other things. He went on to help break the Enigma machine. He was a huge proponent of artificial intelligence. During his time, he actually really didn't even realize how influential this original paper was, and didn't realize kind of spawning of a whole new, academic area. So Alan Turing was a scientist, and he was an accidental computer scientist. He's not unique. Most of the greatest inventions in life are born of necessity. It's not necessarily somebody just sitting in a room away from everybody else, just trying to think, all right, I'm gonna be great. Like think really hard. Am I great yet? No, keep thinking. So I want to share a customer story that is vaguely related to this in some way, shape, or form. So again, I work at Heroku, and one day we had a ticket that came in, and I get this all the time. Somebody's like, "Hey, my app is like really slow," and I'm like, "Okay, well, I'm going to check the metrics." And when I did that, I saw, if you look down at the bottom, there's this like red stuff that is not really good when it's coming to RAM. That's showing swap. So swap is whenever your operating system starts writing to disk as opposed to using RAM. So, all right, okay, we're using way too much RAM. Why? Well, I asked the customer, and they were like, it didn't used to happen, and obviously we didn't change anything. I was like, oh, okay, great, done. It's obviously our fault. Sorry. So I want to introduce the concept that slow is a bug. This is something a lot of people, whenever they hear of performance problems, they kind of like freak out and they're like, oh, I've never dealt with a performance problem before. Like, how do I do this? Well, slowness is a bug, and bugs can be reproduced. So we can figure out why this is happening, and once we can reproduce it, then we can squash it. So let's use science. Obviously, scientists have to have hypotheses. So my first hypothesis was that the RAM increase was due to a bad gem. If they're like, oh yeah, I haven't changed anything, it's like, well, almost every time somebody says that, I guarantee their gem_file.lock has changed. Just like every time. So how can we test this? I was like, well, it would be amazing if we could just boot the app, hit it with a bunch of requests, and see if see what happens with memory. I was like, okay. So I took a couple of existing scripts that were out there on the internet and kind of wrapped them up into a package to help me do that without actually having to, like, say, deploy to a server. So I could actually do those actions. Boot the app, hit it with requests, and do some sort of benchmarking on it locally. And then I found this animation, and I was like, I have the perfect name for this library. So, okay, boot the app, process request, benchmark with memory profiler. Has anybody used memory profiler before? Terrence Lee, ladies and gentlemen. Terrence Lee used memory profiler. So it is a gem by Sam Saffron, which is a brilliant man. And so basically I just he already has this benchmark, and I wrapped it up, and so now you can run rake perf mem. And when I did that, I saw, hey, look, it looks like rack is using a bunch of objects, and action pack, and oh, what's this hashy thing? I don't know if anybody knows this, but I love hashy. It's like super sarcasm. So hashy is incredibly expensive. Each time you initialize it, it just creates tons and tons of junk objects. And I asked them about it, and they were like, "Oh, we're not using hashy for anything." And at the end of the day, it turns out that Omniauth actually uses hashy. The creator of Omniauth is also the creator of hashy, which kind of makes sense that you would use your own things. This was mitigated in Omniauth 7.7.4, where basically I just memoized some stuff. It wasn't like we were even going through the Omniauth flow. It was just like a random page that wasn't even touching Omniauth. And Omniauth was still creating almost the most amount of objects by far. So we mitigated this and updated the client's customer's gem_file.lock. And the app is still over the RAM limit. Okay, so as a scientist, we have to have another hypothesis. So the second hypothesis was that a gem got bumped or changed somehow that was it was adding too much memory at boot time. Like that's a common thing that we request to customers who are like, oh yeah, boot time is really slow. It's like, well, hey, maybe go through your gem file.lock or your gem file and prune gems that you're not using. It's really common. Somebody will be like, hey, this cool gem just came out, and they stick it in their gem file.lock, use it for like a day, and then never use it again. So how do we actually test this? How do we actually see how much memory each of our gems is using? So there was no existing benchmark library for this. And so we have to write one. Conceptually, if we can measure the RAM before and after each require, then we can report it. That's the basic gist of it. To actually do that, we're going to use a gem called get process mem. It basically just shells out the PS, which is available on most operating systems, and it's going to return the RSS, or resident set size. So memory is really, really tricky. Like a lot of times you might just think of memory in terms of, hey, this program uses 14 megabytes of RAM. But realistically, most operating systems have no idea how much memory that program is actually using. So RSS is actually I would say, closest approximation of memory use. It doesn't take into account shared memory. It doesn't take into account anything like the operating system's overcommit or like how it's paging things. So in order to dig in there and actually measure this, I monkey patched kernel.require. It looks something kind of like this, and then I booted an app, and I just output like, hey, for every single file, we're also going to output like before and after, before minus after, and we can see here that will paginate active record requires 1.49 megs of RAM. It's like, okay, well that's good to know, but what of these is using the most amount of RAM? In their application, it turned out to be the mail gem. So mail was using 39 megabytes, which is kind of a lot. I think, yes, overall it accounted for 65% of the entire application's memory use on boot time, which, again, I think is a little high. And again, we haven't even done any work. We haven't even processed any requests. We haven't really initialized many objects. It's not like this is the 1,000th request. This is just at boot. So why? Again, it's kind of like this constant process of get a little bit of information, keep on asking more questions. Get a little bit of information, more questions. So we're gonna dig deeper, because when you require mail, it doesn't just it's not just like, oh, the mail gem is really big. Mail is going to require other files, and we need a little bit more visibility. When you require a file, it's going to act a little bit like a tree. Each node can have many children, and then each one of those children has a cost. It looks something kind of like this. So mail is going to require MIME types, which is an insanely expensive gem. Which is going to require MIME type, and that's going to require MIME and JSON, and so on and so forth. And it just goes like this. So it'll go down all the way down one of those, and then kind of back up, and then down the next, and then back up and down the next. So here is the object that I use to store that information. We can just create a require tree. It's named mail, and then we can just create another require tree, and that's essentially a node, and we can just stuff that into the mail gem. And you can just keep on going and going and going. So once we have this information, we can sort the children and print the cost recursively. It just looks kind of something like this. And the final version of the code is this is actually what ended up being in production and in the derailed benchmarks. We're going to instantiate a node. So for example, this is going to be the mail gem, and then we need to figure out its parent. So this is the last thing that we push onto a stack that we're keeping track of. This might be Rails or rail ties. So Rails require the mail gem. We push that onto the parent as a child node, and then we push the current node, such as, in this example, we're using mail. So mail would be pushed onto our stack, which keeps track of how deep we are in that tree. Then finally, we figure out how much memory we're currently using, and then we do the actual require. Notice we have a begin and ensure block here. That's because people do some really funky things with requires. Like a lot of people actually use require raising exception as flow control. They might expect a load error. So if we don't have the ensure here, like it took me a really long time to figure this out, it'll kind of screw things up. So once require has returned, we pop this element off the stack. So we say, okay, we've recursively recalled all of the other requires inside of mail gem. We're done. Now we're going to pop mail off, and we are going to record the memory. Finally, we're going to record the cost, and we're done. So we do this recursively for every single require in the entire application as we boot up and hit a request, and the final output is going to look something kind of like this. And we can see that inside of the mail gem, mail parsers is really expensive. So mail parsers is taking up 19 megabytes. From here, I ended up opening up an issue. I didn't actually solve this one, but somebody else on the mail team was like, hey, yeah, that doesn't look right. And it turns out that they changed the way that they were doing the mail parsers. Inside of the mail gem, you can actually, instead of just sending out mail, you can also receive mail. You know how GitHub has that, you just reply to an email from GitHub and it like turns into something? Well, they, and you can ask Donish if it actually is the mail gem, but they'll take something like the mail gem and parse it and say, okay, here's the subject line, here's the body, oh, here's the actual new response, and do something with that. So most applications aren't actually doing anything with parsing mail, so they don't actually need it. But those that are, it's extremely performance sensitive. And inside of mail, they rewrote the parsing code to be, I forget exactly how much faster, but extraordinarily faster, light years faster. Unfortunately, doing so also made it much, much, much more, even just loading up the parser, much heavier. So it doesn't make any sense to by default load the parser for every single user in Ruby, or in using the mail gem. This was fixed in number 817 in the mail gem, and we saw the customer's app use, RAM use drop dramatically. No longer swapping, and then slow, now they're fast. It's that simple. So we want to reproduce slowness to a bug, we want to get visibility, and use science. Seems pretty reasonable. Okay. Before you get too excited, I want to talk about a problem in open source. There is trouble brewing under the water. There's kind of this perception problem. The perception problem might be that I read Hacker News sometimes, but I run into this a lot where we have people that have this common idea and this common thread of, hey, wouldn't it be great if more people worked on open source full time? Like some company somewhere should totally sponsor that. And they're always like, hey, GitHub or like Heroku should sponsor that. And I'm like, hey, we hired Koichi and Matsunobu. Thank you for noticing. Thank you, Koichi. And yeah, there's this kind of meme of company X should sponsor more open source. So keep that in mind. And I have a related question. Have you ever made a bad deploy on a Friday? Okay, I'm gonna take that as a yes. Like it's one of those things where you like try to fix it and then you deploy the fix and then it's like, oh no, another bug. And then your weekend is just like gone, and your coworker's weekend is just like gone, and you have support staff, they're just like, why am I here? So as always, I ask myself, is there a better way? I have a very modest proposal. Don't deploy on Fridays. Just don't. And you might be like, okay, sold. But like, what am I going to do? Just play like, Pokemon or something? Instead, what I recommend is I'm calling Funday Friday, and this is actually something that we've kind of done at Heroku. Sort of. I'll get to that in a second. But all right, is your application slow? Wouldn't it be amazing if you had some time on Friday to be like, all right, yeah, we'll look at this instead of just being like, okay, hey, we're going to spend 4 months making our application fast, and then your boss is like, hey, you should do that. And then you get like 2 days into it, and your boss is like, oh yeah, by the way, here's 10 features you also need to add. It's like, oh, thanks. What about if your app is disorganized? Funday Friday. You ever like, hey, I really need to refactor this code, and your boss is like, great, you should do that, and then you never get any time for it? It's like, what if you did it on Friday? Do you personally ever wish that company X or Y sponsored open source? Well, I have really good news for you. Because your company just sponsored you to work on open source on Fridays. Life changed. You might be thinking like, okay, yeah, this sounds like fun, and like I obviously like this, but yeah, my boss is totally not going to go for this. My coworkers are totally not going to go for this. I actually think it gives you more accurate deadlines. If instead of like sometimes you're working on a real critical feature and you're like, oh, this is not going to I just have to spend half of the time. I have to spend half a week refactoring before I can even go anywhere. What if you just baked in that refactoring time a little bit every single week? What if you had less burnout in your office place, and you had less people constantly asking and saying like, hey, where's all that code? Or if your boss is ever like, hey, we want to hire more senior developers. I want to hire the kind of people who refactor and make speed improvements and knows library internals and contributes to open source. It's like, okay, well, one of the ways to do that would be to allow your coworkers to do these things. And you can actually train up senior developers and like kind of level up and power up your own developers. So yeah, Funday Friday. And it's kind of a 3-part program. The first part is to do this. The second part is to report your progress to your team. Like I said, at Heroku, I kind of started doing this because I broke something really bad on Friday once and made support stay really late, and I was like, never again. And then guess what? I started reporting my team and being like, hey, there's this really cool patch I made to Rack, there's this really cool patch I made to Rails, and they're like, you're amazing, that's really cool. And then they had questions on those open source libraries, and I reported it to my boss, and she got really excited, and she started saying, like, congratulations and good job. So that's the first 2 steps. I also want you to report it onto Twitter, #FundayFriday. This is a new thing. I've not started doing this yet, but I totally will. And ideally, you can get love, even if it's an internal thing. Even if it's like, hey, I spent the entire day on performance and I didn't get anything done. Guess what? You just learned what not to do, and next Friday maybe you'll get a little further. So if you see somebody tweeting out with this hashtag, no matter what they did, just be like, that's amazing, I love it, and give love. So yes, all right, I think I'm out of time. Okay, here we go. So we need you to participate, we need you to create, we need you to science. Thank you very much.